My name is Thomas Russell. I'm a Senior Sales Application Engineer at ABB. I've been working in the variable frequency drive business in the HVAC and industrial market for over 25 years. This is part of the Energy Savings Series, Drive and Fan Curves. This webinar focuses on the basic understanding of fan applications and the cost savings potential of using variable frequency drives. Subjects covered are constant speed, control of airflow, affinity laws, otherwise known as fan laws, and the relationship of fan performance and power, energy savings by the use of adjustable speed drives on fan systems, benefits of ABB drives, and features that support energy savings and monitoring. The agenda is we're going to look at fan curves, non-VFD system review, variable frequency drives, fundamentals, affinity laws, and for variable speed fan control, variable frequency drives, and features. Let's take a look at fan curves. Fan performance curves, system performance curves, operating point, looking at a fan performance curve, it's supplied by the manufacturer for a specific fan. The relationship between the amount of air the fan will deliver versus pressure, where vertical is pressure, P, and horizontal is flow, Q. The fan speed in RPM relationship to pressure and flow is graphed. The brake horsepower relationship to pressure and flow is graphed and showed here as dotted lines. The usable fan range is shown. You do not want to go left of the system curves from the usable fan range. Other items like efficiency, noise levels, impeller tip speed may also be shown. Let's look at a system performance curve. When a manufacturer decides to test a fan, they hook it up on a test system, and the first thing they do is determine the maximum flow. And this is no system pressure. The fan's running through a set of ductwork, it's open-ended, and you get the maximum flow through the ductwork. For static, no flow, otherwise max pressure, they cap the end of the ductwork, and the fans ran up to full speed, and we find out how much pressure you can get, but there's no airflow. When this is graphed, from the maximum flow to the static no flow section, the manufacturer will discover where a stall region occurs, and this is where the fan becomes unstable. The operation range manufacturer specified is pressure versus flow, and this is the range that fan is designed to operate in. System resistance is the total of all pressures losses throughout the system. Ducts, elbows, dampers, coils, filters, and any other device that restricts flow is added up to create the system resistance. System curves is how the system will react to a given airflow. The fan will run at a point where the system resistance curve intersects the fan curve, and the system curve will change as the system resistance changes. Let's look at the operating point. P equals pressure. Pressure is on the vertical of the graph, and it's shown in percentage. We're going to use percentages to normalize our results. K is a constant based on the system resistance. The value of K will be low on low resistive systems. The value of K will be high on high resistive systems. Q is flow. Flow is shown in a percentage on the horizontal part of the graph. Pressure equals the constant times flow squared. So P equals K times Q squared. The operating point is based on the system resistance, the pressure versus flow, as shown. Where this point means the fan curve, this is called the operational point. Let's review some non-VFD systems. We'll look at a system load profile, on-off control of a system, and an outlet damper control. System load profile. In our example, we're going to look at an HVAC system. HVAC systems are designed for the worst case situations, the coldest days in winter and the hottest, most humid days in summer with the highest occupancy. All other times, the HVAC system is oversized. Most of the time, the load is between 45 and 70%. The fan is sized for 100% of the load, which is only 1 or 2% of the time. Other processes have varying duty cycles. So the system load profile we're going to look at for our example, shown here, 10% of the time the system is running on 100%. 35% of the time the system's at 80%. 45% of the time the system's at 60%. And 10% of the time the system's at 40%. We're going to use this as a load profile for our calculations for our future examples. So looking at on and off control. The fan is turned on and off as needed to produce the average flow. There's no flow control, only average flow over time. The average flow is based on the duty cycle over time. Power surges are at each startup and need to be added up. The simplest type of control, it's inefficient and causes pulse flow. It's common in home heating and cooling, and it's good for large volume areas. It's not good for most industrial applications though. Let's look at outlet damper control. Dampers are opened and closed as needed to control flow. As the dampers are open, the pressure P decreases and the flow Q increases. As the dampers are closed, the pressure P increases and the flow Q decreases. This is the pressure on the fan itself. This allows for flow control for industrial HVAC applications. So let's look at the fan and flow control with dampers. Flow is controlled by adjusting the dampers. Consider the dampers as part of the load. As the damper closes, the pressure increases on the fan and the flow is reduced. The dampers can be considered part of the load, increasing the K value as it's closing. As the dampers close, the system curve is shifting to the left, as shown. As the curve shifts to the left, energy is equal to the area of pressure times flow, P times Q, as shown. So let's look at initially, before we start closing the dampers, the energy is shown green. As we start closing the dampers, the pressure increases, and we have a new energy area. And when we get to the final point on our graph in red, this is the new area of energy that's being consumed. This does not save much energy, but it's a simple solution. So looking at flow control with dampers, we can look at the flow and the horsepower. The power curve does depend on the fan characteristics and brake horsepower. So it's a BHP, which is a brake horsepower. A 20% reduction in load creates about a 5% reduction in brake horsepower in this case. And a 40% reduction in load creates about a 17% power reduction in your brake horsepower. And this is shown by this graph here for power and horsepower over percentage of flow. The flow is reducing, but little energy is saved and realized. Let's look at flow control with dampers and do some example calculations. So at 100% flow, and our duty cycle of 10% of the time, our system is designed for a 25 horsepower brake horsepower. So at 10% of the time, 25 horsepower times 0.1 equals 2.5. That's your weighted horsepower. Looking at 80% flow at 35% of the time, because we've closed our dampers to reduce our flow, that's caused an increase of pressure on the fan itself. Our brake horsepower has dropped down to 24 horsepower, and our weighted horsepower comes out to 8.4. So 60% flow, 45% of the time, this reduces our brake horsepower down to 21 horsepower. And calculating that out, our weighted horsepower comes out to 9.5. And at 40% flow, 10% of the time, our brake horsepower is reduced down to 17 horsepower, giving us a weighted horsepower of 1.7. This totals out to a total of 22.1 horsepower as your average horsepower on your system. There's not much cost savings here, but there is a cost savings. The system was designed for 25 horsepower, but because the way the system works, by using dampers and causing increased pressure on the fan, reducing the efficiency of the fan, it also unloads the fan in a way that the horsepower that's needed drops. You get a total horsepower of an average. Now let's do an overview of the fundamentals of a variable frequency drive. Let's look at what happens inside of a VFD. What is pulse width modulation, PWM, and the output frequency and amplitude of a drive. So let's look at what happens inside of a VFD. The input power being applied to this drawing is 460 volts, 60 hertz AC, 3-phase. It arrives at the rectifier, which is a diode bridge. This is a 6-pulse bridge. There's 6 diodes. It's converted to DC, which converted 460 volt AC comes out to about 650 volts DC, and it's stored on the DC bus. The inverters, the IGBTs, pulse width modulate the output to create a new voltage and a new output frequency. Looking at the output of the drive, the IGBTs act like switches. We'll look at one phase here. As the IGBT turns on to the positive side of the DC bus, we have a positive pulse coming out of the drive. As we turn to the negative side, we get a negative pulse. This creates basically a square wave. This would not be much help to run a motor, but we do more than this on the output of the drive. As we pulse width modulate the output of the drive using the IGBTs, we turn the IGBT on for longer and longer periods, and then reduce the period time down to a shorter time, and then eventually we complete the positive side of the waveform, and we complete the negative side of the waveform. How often you switch from positive pulses to negative pulses determines the frequency of the waveform. How much time you spend on and off determines the voltage. For a frequency of 30 Hz, as shown on the left, or a frequency of 60 Hz, as shown on the right, it is shown by a pulse width modulation. The output of the drive to the motor, for high speeds, we need a higher voltage with a higher frequency, and if you want to slow the motor down, you change your voltage to a lower voltage with a lower frequency. Let's look at the affinity laws for variable speed fan control. Affinity laws are also known as fan laws and pump laws. We'll review variable torque loads. We will review the fan curves and VFD control. VFD control examples and calculations will be shown. Flow versus speed. According to the affinity laws, the change of flow is equal to the change of speed. As we're showing here in percentages, flow is on the vertical and speed is on the horizontal. Flow is directly proportional to the speed of the fan. Pressure versus speed. Looking at pressure, the change in pressure is equal to the change in speed squared. Pressure is proportional to the square of speed. And power versus speed. Looking at power and horsepower versus the speed, horsepower, change in horsepower is equal to the cube of the change in speed. The power is proportional to the cube of speed. Constant and variable torque applications. There are 3 basic types of mechanical loads that are encountered in an AC drive system. Constant torque, CT, i.e. conveyors. Variable torque, VT, centrifuge fans and pumps. And constant horsepower, which would be used in machine tools. Looking at constant torque is a uniform torque requirements across the motor's speed range. Relatively high torque at low speeds compared to the fan and pump. A conveyor belt, hoist, and mixers have constant torque applications. The affinity laws do not apply to constant torque applications. For variable torque loads, the speed control relationship, the drive can change the speed of the motor. By reducing the motor speed, the fan curve is moved. In variable torque loads, flow Q varies linearly with speed, as explained earlier. Pressure P, or the torque, varies to the square of speed. And power and horsepower varies to the cube of speed. Fan, blowers, pumps are variable torque loads. The affinity laws do apply to variable torque load applications. Looking at the fan curve, at full speed, the operation point is where the system control curve meets the fan curve. The VFD can change the speed of the fan. The fan curve shifts the speed N changes from N1 to N2, then from N2 to N3. N1 is greater than N2, N2 is greater than N3. the operation point changes along the system's control curves. So at speed N1, full speed, you get 100% pressure with 100% flow. As you go to N2, you reduce in pressure and you reduce in flow. As you go down to N3, you reduce in pressure and you reduce in flow even more. Look at the affinity laws. The flow Q is directly proportional to the speed, so Q can be replaced with N. From there, we have P2 over P1 for pressure equal to Q2 over Q1 squared. At this point, we can solve for P2. By solving for P2, pressure 2 is equal to pressure 1 times Q2 over Q1 squared. So looking at our system, as speed is reduced, flow Q is reduced, and pressure is reduced. The pressure is dropping by the flow Q squared. The energy is the area equal to the area of pressure times flow, P times Q. The area under N3 is much reduced because pressure is reduced compared to flow control, which we looked at earlier. The area under N2 is much reduced compared to flow control also. And the area under N1 is at full 100% pressure and 100% flow. So let's look at the affinity laws and look at horsepower. We said earlier that the change in flow is equal to the change in speed. It's directly proportional. When we look at the horsepower formula, the change in horsepower is equal to the change in speed cubed. So we can replace N with Q. By doing this, we have the change in horsepower is equal to the change in flow cubed. Solving for your horsepower 2. Horsepower 2 equals horsepower 1 times Q2 over Q1 cubed. Let's apply that math directly to these curves shown here in percentages. So looking at the power curve, we're looking at horsepower along the vertical right now and flow along the horizontal. Not pressure on the vertical. This is horsepower. This is all done in percentages to normalize the system. So the band of power increases with the cube of speed. The formula we just showed earlier is horsepower 2 equals horsepower 1, which is Q2, the ratio Q2 over Q1 cubed. So we're going to use Q1 at 100% or 1. And we have our horsepower for our motor at 25 horsepower. That's horsepower 1. When we solved for horsepower 2, we had horsepower 1 times Q2 over Q1 cubed. Now remember, Q1 is starting at 100%. So Q2, whatever it is, over Q1, Q1 is 1. So let's look at 50% speed. That is horsepower 2 equals 25 horsepower times 0.5 divided by 1 cubed. So that's 25 horsepower times 0.125, which equals 3.125 horsepower. This is the effect that you have by the cube law. Running a fan at half speed consumes only 1/8 the power compared to running a fan at full speed. Let's look at the VFD control example calculations for applying the fan laws. Horsepower 2 equals horsepower 1 times the change in flow cubed. Now Q1 is always going to be 100% because we're normalizing at 100%. And horsepower 1 is always going to be 25 horsepower because that's your system. So with Q2 at 100%, that's 100% 1 over 1. So it's 1 cubed. So 25 horsepower times 1 cubed, which equals 25 horsepower times 1, which equals 25 horsepower. In this case here, at 100% load, 100% flow, we are loaded at 25 horsepower. Now we're going to change our flow to 80%. So that's 25 horsepower times 0.08 cubed. So 25 horsepower times 0.512 equals 12.8 horsepower. So at 80% flow, our system is calling for 12.8 horsepower. Then at 60% flow, recalculating out that, we come up with 5.4 horsepower. And at 40% flow, doing the calculations, we come out with 1.6 horsepower. So if we take our CFM on our same duty cycle that we had before, for our example earlier, and we're going to use our horsepowers we just calculated out and calculate out the weighted horsepowers. So an example calculation, 100% Q, which is 100% flow, happens only 10% of the time. And our horsepower at 100% was 25 horsepower. So our weighted horsepower is 2.5 horsepower. Compared to damper control, the outlet damper control, this has not changed. At 80% of flow, 35% of the time, our new horsepower that's being loaded down by the fan, because we've slowed the fan down and we've changed the RPM of the fan, is 12.8 horsepower, which gives us, at 35% of the time, a weighted horsepower of 4.48 horsepower. At 60% flow, 45% of the time, we're at 5.4 horsepower because we've slowed down the fan even more. And at 45% of the time, 5.4 horsepower equals 2.43 horsepower. Then at 40% flow, 10% of the time, and we're only demanding 1.6 horsepower, we end up with 0.16 horsepower. When we total up our weighted horsepower of our system, over our duty cycle of our system, we have an average of 9.57 horsepower. Compared to the 22 horsepower from the damper system, with the outlet dampers, this is a great reduction with a large power savings. All right, let's do simple calculations of how much energy is being consumed between the difference between outlet damper control and variable frequency drive control. So the outlet dampers had a total weighted horsepower of 22.1 horsepower, and variable frequency drive control had a total weighted horsepower of 9.57 horsepower. If you want to get yourself the kilowatts, you multiply by 0.746, and you want to look at your full month of how much you can consume. That's 730 hours in a month. You multiply it all together, your horsepower times your kilowatts times your hours per month, you'll get your kilowatt hours per month, and that's for outlet damper control, that's 12,035 kilowatt hours per month. But for variable frequency drive control, you're down to 5,212 kilowatt hours per month. So let's just say we're going to do 12 cents a kilowatt. That means your total cost per month is $1,444 for outlet damper control and $625 for variable frequency drive control. The total savings, if this is what you ran all the time, for your average duty cycle and everything else, would be $819 per month using the VFD. Now, cost varies by location and time of day. On peak could be 12 cents per kilowatt hour. Off peak could be 6 cents per kilowatt hour. I'm not compensating for any of that in this chart here. This is just basically showing you a basic idea of where the math goes. Future environmental savings and requirements should always be considered. The fact that adding a drive to a system not only saves energy, it helps the environment. Reducing your power reduces your CO2 footprint, and that can also be considered. Let's look at some variable frequency drive features. Note that the ABB ACH 580s, the ACS 580s, and the ACQ 580 drive families are used for this next section. Many ABB drives have similar features, and some other drive manufacturers have the same features too. We're going to look at displaying cost savings, energy efficiency menus, and energy optimization. Drives can be programmed to display multiple parameters. As shown here, we have the savings amount in dollars on the first line, the savings in kilowatt hours on the second line, and the savings in total savings of CO2. All information is available to communication systems and to allow the building management system to collect all this data. The control panel has multiple screens that can be programmed from multiple different ways. There's multiple lines per screen. Different display types can be shown. Moving from screen to screen is simple. You just use the left and right arrows. The 580 series display has a quick display menu to help you set up different displayed items that are commonly used. Saved kilowatt hours, saved gigawatt hours, saved megawatt hours, saved amount of dollars, saved amount of thousands of dollars, CO2 reduction in tons, your total saved CO2, inverter kilowatt hours can also be displayed, megawatt hours for the inverter, and gigawatt hours for the inverter. They're all counters. And there's other things you can select that you can add on to bring up to your display easily. One thing to remember is on these drive series, you can pretty much go to any parameter you want, and you can display any parameter in multiple different ways. Your display settings can be changed. They can be numeric, gauges and bars, and you can graph anywhere from 15 minutes to 24 hours of operation. The display names can be changed up to 50 characters. Units can be labeled up to 50 different characters. If you're doing some math and you want to have different units, you can display whatever units you want, and you can actually have your own units. And depending on parameter selections, your minimum maximums and certain parameters like kilowatt hours, it's 21 million. It's over 21 million. So if you're running over 21 million kilowatt hours or megawatt hours, you've definitely been running for a long time. And your selectable minimum maximums are over 21 million negative to over 21 million positive. So there's a very, very large range for these drives. So energy efficiency menu. The energy efficiency menu allows for viewing of energy and power values, viewing and changing settings for load analyzers, and amplitude peaks and value logger settings. You can change energy calculation settings in the energy efficiency menus. Your total energy saved in kilowatt hours compared to directly across the line motors. So when your drive is showing your total energy saved in kilowatt hours, it's comparing what would happen if that motor was being ran across the line. And the corresponding money saved is depending on how much money you put into, how much it costs per kilowatt hour, and your CO2, that's also calculated too. The energy used in your energy efficiency selections is the energy used in the last hour, the last day, or the last month, and the used total. The peak power, you have hourly peak power and what time the hourly peak power occurs, the daily peak power and what time and day of the day occurs, the monthly peak power with time and date, and all-time peak power with time and date. So these energy items are you can track and you can find out when you're taking your total peak power, and you can look at your system and see if you want to change your system in a way to start saving more energy. So you can create your load profiles. Your amplitude logger 1 and 2 are graphical representations, can be shown. And your amplitude loggers can be shown in distributed diagrams. You can find out what running time was spent at each load level. Your load profile configuration can be downloaded. Your peak value logger and list of maximum momentary loads is all there. So you can have all that data to determine how your system is working and determine what load profiles you actually have. In your calculation settings, you can calculate out your energy optimizer. You can look at energy tariffs for changes in price of kilowatt, per kilowatt hour. You can have different times and you put up different tariffs for multipliers and have different selections. And your CO2 conversion and your comparison of power can all be programmed. Energy optimization function. The function optimizes the motor flux so that the total energy consumption and motor noise levels are reduced when the drive is operating below the nominal load. The total energy efficiency of the motor and drive can be improved by 1 to 20% depending on the load, torque, and speed characteristics of your system. This is done through only supplying the needed voltage to support the needed torque at that time and actively changing it as the torques change. Energy optimization is on by default. So let's review what we've gone through. We've looked at fan curves. We've looked at a non-VFD system review. We looked at variable frequency drive fundamentals. We talked about the affinity laws and variable speed fan control. We looked at variable frequency drive features. Thank you. This concludes our presentation.